Okay.
It's my pleasure to introduce Mingyuan, who will tell us about cylindrical KLRW algebras and not homology.
Okay, yeah, thanks for the introduction. Well, so my plan was to first give a brief introduction on like not homology. But probably like most people in the audience are familiar with this concept, so maybe I'll go very fast since I wasn't sure if I should talk about this, but there's a whole lecture about this topic in the MIT summer school, so probably I'll go over this very quick. So first, well, you have some classical non-invariants like John's polynomial. Right, this is given by, well, you have a null, and then you define some relation, like there's minus t as if you define such relation, then maybe every link, well, in R3, this will be sent to a polynomial. Probably here you need to ask the unknown to be one in this case. So, well, this means whenever you have a link, and then you can use this like scheme relation to to reduce a node to a link to some polynomial. So this is the invariant on the red mass moves. So it's a link invariant, and then, well,
Learning what you broke the relation, but what are the generators over what are we working?
because the generators are all the links.
All the links.
All the links in R3, right?
And the coefficients are in what you wrote.
Oh, sorry, I actually write down. So sorry, I actually explain more. So, well, yeah. So you consider the free CP module, or sorry, yes. You consider the free CCP module generated by all the isotopy class of links in R3, and then quotient out this relation. And the theorem is that this module is going to just going to be this this ring, which means when every link is equivalent to a polynomial under this relation, and that's just polynomial. Any question for this? Well, this. So probably you ask what's the generalization of this. And then one way to do this is to use like representation of quantum groups. So, and now let's define category, which called the category of tangles. This is going to be a category, and the objects are like points on a line on R, and it's the minus plus and minus. There are some signs like sign points on a real line, and then most of them are just tangles. For example, I have two objects here, plus then it's well, so actually this lives in dimension 3. So you have two types of crossing, and maybe you have plus, minus, right? And then composition is just you stack two tangles, one on the top, the other on the bottom, whatever, something like that. This is plus, and if you have a minus here, so right, that's the model.
Sorry. How do plus and minus is more?
Oh, it's like on the plus, everything's pointing. On the bottom, like plus means pointing upward, like minus means pointing downward. So here it's pointing downward, right? Plus pointing upward. Yep. And then we will find that the home. Oh, this is the monoidal category, and the home between, well, empty means like there are no points on this line, and that's a like unit object in this monoidal category, and this is going to be the isotopic class of all links in R3, right?
So you allow it there. You also allow like circles, but not.
Yes, there could be circles, of course. And then
And therefore we like orienting circle.
yes, because like circle is just the composition of this one and that one. That's the composition of this two. Link. So for any link, you can just like decompose the link into some, simple, like simple morphism, which is crossing and then this, half circle. And then. Sorry, what's the question?
So a link could be the direction.
Yeah, a link, like oriented link.
Sorry.
Oh, sorry, I mean, oriented, hey, maybe I should say this is like oriented links. Oh, yeah. Okay. And then, well, if you have a functor, here, let's say, consider that vector space, maybe over here, over CQ, this one parameter from parameter Q. If you have such a functor, and then in particular, you will send links. And that side is going to be home. MP. No, of course. Well, this is monoidal category, so I assume this functor is monoidal. So then it will send the unit element to the unit element. It will send you to, this two, just two. It's the whole space between. Oh, here the unit object is just a CQ, like one-dimensional vector space, and it's the anamorphism space. It's this. And such a functor can be realized by Coulomb groups. So, well, theorem that any representation of a Coulomb group will induce such a functor. To be honest, I don't know who first proved this. Like, is it Richard Tiken? And I don't know. Yeah, maybe that's what we like. Anyway, so the idea is that well, if I have such a representation, then plus minus, it's going to be sent. It's going to be sent to class is sent to V, and then minus is sent to zero V, and then well, if you have crossing, right, and this is like a positive crossing, it's going to be sent to the R matrix from this presentation. Then the little bit harder part is this, we have this cap and cap and also this and they are given by the they're given by algebra structure. Yeah, I won't go to detail this. I think last quarter, maybe car. Oh, not last quarter. That's year. Car give a talk on this topic in Eric's class or something like that. So, and then maybe I should say that well, if so, this UQ has two. Well, gives you the Jones polynomial.
Here's your tools, basically.
Sorry, what?
You
Oh yeah, well, with the like basic representation as like two. Yeah, that's
well, it's fine. You can. I mean,
okay.
I do it
Yeah,
with you.
thanks. Then, well, and maybe you'll notice that I wrote vector space there. So if you like categories, so probably you don't really like that. So the one natural question is to ask is how do you categorify? Right, uh, and then first I think no, yeah. Okay, first to give a like combinatorial way to define like for now to define a chain complex. It's bi-graded chain complex. Which is later called Coulomb homology, and this is defined by knot diagram. So basically, you have a knot and a hotel. For every knot, for every crossing, there's like two way to resolve this crossing, and then well, then you take like some linear combination. This gives you this bi-graded chain complex. It's defined in a combinatorial way. And one important feature is let me see where I should put the degree. There. Okay. So the Jones polynomial is going to be, well, here's here you'll fix you'll fix the second degree. And then you'll take Euler characteristic. This means like you take dimension of like alternative like you dimension. You'll take alternative sum of the dimension as well, right? You have chain complex in this Euler number, and then you take sum. So then that will recover your Jones polynomial. So here, this chi means you take sum over the first degree, and then you take sum over this second degree. This Q recalls like second degree. That's yeah. But maybe this is well. I mean, this is like great. Like progress in this direction. However, maybe it's not that satisfactory since this is kind of like ad hoc. You have a knot diagram and everything's defined combinatorially. So maybe one could ask if you can if you okay you can define maybe how to define homology. Somehow universal way. It's just like what we did before, right? So for any, you give a functor, and then I get a non-polynomial. And then, well, there are many ways to do this, but probably today I want to follow Aganagic's idea. Well, so in the I think it's 2022's ICM talk, and she well, actually she's papers like earlier than that, but I mean, she said this can be done by two ways. One is you consider the coherent shapes on some modular space, but I mean, she's language is like in physics, but second is some category. The other way, so and they're related by homological universal symmetry. So maybe I actually expand a bit more.
You can just pause here.
Sorry, what?
I think you.
Oh, I actually use this bar. Oh,
Yeah.
sorry. Yeah, thanks. Let me explain. Also, if you want to categorify this, so probably a natural idea is to we want to find a functor from this tangle category to the category. Maybe we want like maybe city in a category. So this is for example, like 2 category, and you want such a functor. If you have such a functor, and then the links. This is code like empty will be sent to code, the chain complex. Chain complex will be saved. Here is the monoidal. The union of this monoidal category is going to be the chain complex over C, and then so any link here is going to be sent to a like bi-derivative income. So why? Well, isn't this just let's say, wait, isn't this just bi-gradation complex?
I think that homomorphism from development.
Yeah,
Unless you call it defined, like you can define it to preserve the degree, you can define that there are some of all where.
Oh, yeah. So
yeah, the issue is we didn't define the categories, maybe.
yeah. Oh, sorry. Which one? Like
Cat C.
Let's say. Sorry, I'm being like very not being precise here, but I'm thinking about like C linear or maybe category enriched over chain complex over C. Oh, maybe
If you want the homospace for a chain, structure of a chain complex, then you want the morphism to be morphism of chain complexes.
yeah, morphism.
Like you don't want that here. You want to allow morphisms that do not preserve.
What like usually it's category of deep categories or something.
I mean,
Yeah.
cKLRW usually complex is from vector to vector determined by the value of chains.
Yeah, so if this is category
complexes,
Yeah,
it commutes with fine.
Okay. Let us maybe define it precisely if we are going to actually use it, and if not, then save it for an instance again.
So probably I'm sorry, I'm not going to like really use it, but
That's very good.
Yeah, let me think it deep. So if I'm defined this to be like still in a DG category, and then what is this home space? You run into but
In any case, if you want, you can, in any case, you can reach the height, but spaces will be chance, like, if you have this action, like this action of homological shift, and, you know, just can incorporate it into homes if you want, and it seems that you want it, so. Just
yeah.
home.
Yeah, chain group is not as like a derived vector spaces. Like not just think about it.
Oh.
Yes.
Then maybe I want something like recursion by
What was it?
Is that
As moving somehow, but
it's not going to work?
no, you can just say, yeah, I mean, it's like category plus an additional, like a differential, like an extra differential.
Oh,
it's not up to quasi-isomorphism. I'm just saying, as though if we consider chain homology is not up to quasi-isomorphism, but like in a more rigid way, then yeah, then it will be evaluated.
Yeah.
Because we don't want maps to preserve anything.
Maybe we should wait for some example to articulate.
Yeah. Probably, well.
See where it's natural to define.
Yeah.
Where does go?
Well. Oh, sorry, but later I'll give example which is Coulomb branch, but I'm not going to give the, really give you the proof. So probably we still cannot. Oh, that one. I actually looked that. Oh, sorry. Yeah. Oh, sorry, I didn't think the scene details. Sorry about that. So, and yeah, I'll think about that later. All right, so but in Aganagic language, this chi is going to be some, like model of like G model in R3. And which is mathematically is still going to be this Coulomb branch. So obvious standard. And it turns out that Y is also going to be some other Coulomb branch, and they have this like mirrors, they're related by this mirror stage. So okay, now we're going to talk about like the numerical KLRW algebras and we will build not homology theory from this. So wait. Oh, I'm going to use that log. Wait, this is
Yeah.
sorry.
Yeah. If you move here, I can deal with that blackboard.
Okay, thanks. So, well, I'm just going to briefly recall what Sonia has talked about 2 weeks ago. So, that might be a quiver. Probably in this talk, we will assume it's a AB type. Well, it's an example. Also. there's going to be like framing vertex, right? And then my way it's going to be the I. Well, you have a this is like a dimension vector, and W is going to be J. And I mean, this is like for each vertex in this. For each vertex, you have that's like and it's like the sum of the dimensional vectors. Yeah, the dimension on each like vertex and the L is the sum of J. And in the group is going to be the product of like GL. This is like the gauge group, and then we are considering the all. I mean that way is like curly way, and this is the regular way. That's going to be the the quiver representation. So way I, way J, and direct sum. Well, for each like framing vertex, we also have an arrow which corresponds. Oh, maybe not one, but might be many. Oh, here it is. Yeah, it's before this is only one. Something like that, and G and my G has an action on it. Okay. And then we can consider Coulomb branch of this thing.
Certain state.
Oh, sorry, my bad. Just thanks for reminding. Please keep reminding me if I forgot. Sorry. Okay, and then we also need to pick a key using the normalization of G in GLV, and you assume it's unitary. And then first G will act on each home. Well, I am so well. I mean, if we have an edge here, right? So, and then it's unitary. So for each edge, we assume it's x by this d pi I. So beta. So this leaves being x1, and also it acts on this space by, well, we can assume it's like diagonal, so it's going to act by exp and 2 pi I and beta like I. Sorry, there's too many I here. So ik. So k is going to be 1, 2, I. So yeah, that's our setup. Oh,
This is diagonal matrix.
yeah, diagonal matrix, and here, here. Oh, actually, maybe for our purpose to define not homogeneous area, we will, maybe in the ADE type we can also assume like beta E and zero. Oh, that's and then the cylindrical KLR W algebra is going to be defined by the this diagrams. You have some right strands, which is like vertical. In full. So first you should have like this many and the positions their positions are given by this beta ik. So basically this beta ik gives you the position of the right the right strands and it's vertical. So probably we should have an example in mind. Probably this is the A2 paper. All the here, all the this V1, V2, and all one, and then W1, W2. Then there might also be some black or black strands. Well, this is cylindrical just means that I do this side with this one. But the point is that the position of the endpoint of black strands are not fixed. Only the position of the red strands is fixed. Okay. So and also we will have two chemical strands. There might be some like solid dots on this black strands and then this algebra is cylindrical KLRW algebra is denoted by R beta. This is defined by generated by like the linear combination of these diagrams. By diagrams. Portioned by some related. I want to repeat, but well, maybe a remark is that when this beta is not there in once the paper, it also has some ghost strands by which is by dashed like by dashed lines. But I think in this case we don't really need them since it's equivalent to we call this like unflavored like cKLRW algebras. So I think in this case we don't need those two strands. Okay, so the theorem is that well, in this case, in this notation, this is the Coulomb branch. Equivalent to an importance of R beta. And then this is called a non-commutative symplectic resolution. let me explain what it is. Oh, sorry. Sorry.
Yeah, so you are using non-commutative version of this algebra.
Wait, this algebra, I thought it's not commutative. It is not commutative.
No, I mean, like is Coulomb range. Do you have the rotation Coulomb range?
Oh, sorry, what?
Do you have like is it with H bar?
Oh, no H bar, no H bar.
You mean R beta itself is.
Oh yeah, sorry, but this one itself is a non-commutative resolution. This one is a non-commutative version.
Okay, sorry.
It's oh. Explain what it is. E is the idempotent. Yeah. And then so for each, well, recall like the position of the rest strand is fixed, right? So like this, and then for each vertex and then if I here, then I put this black strands here. I mean, actually for each dot is labeled by a vertex, right? It's I here, and then if I only look at the diagram living in this small interval, then that's the usual KLR algebra, because they are labeled by the same vertex and all the relations are the same. So if I only look at this small interval times the small interval times I, and this will gives us an embedding from the neo-hack algebra. Those two. Right. So for each vertex, there is this is the neo-hack maybe of like AI of AI type. There is such a map, and then we pick some the idempotent elements here, and then it's this by something like hack, and then this E is defined to be the product of all over I So you can imagine it looks like here is like the diagram corresponding to the idempotent elements, and then there's some other, here's other thing, something like that. This is labeled by maybe J, this is labeled by K. Then you put them like parallel to each other, and then that's that idempotent element. The theorem is that this is oh, I'm sorry. I'm so sorry. I'll try to remember this. Yeah. So, but now one question you could ask is that what if we change this beta, right? Okay. So, well, if you here, like the reference is fixed, right? So if you have different data, well, so so one thing you can get is you just take the linear transformation from beta to beta prime, right? If you consider this family, beta plus t times beta prime, then this will gives you a like configuration of the red points, and that's going to be some strict lines, but it's not vertical. Something like that. Right. And then we can consider then this you consider the linear algebra of such diagrams. It's not going to be algebra anymore. It's just a module, right? So like b beta prime, this is defined to be linear combination of such diagram model relation. So because the restaurants that do not really match your in general, so it's so in general it's not going to be an algebra. However, this is going to be it's going to be r beta prime bind module. Because you can stack like r beta module on the bottom and like r beta, so like cylindrical KLR diagram of beta on the bottom, and you can put another like beta prime diagram on the top. So and that's so this gives you the bimodule structure.
Mhm.
And of course, you can think about this. B beta prime tensor, this conquer will send our beta mod to prime mod. Well, in general, this is not going to be isomorphism, but if you consider the derived category, so this is isomorphism. So I mean, well, for AD equivers, yes. In general, I think I said this is still a conjecture, but yeah. And then, well, this tells you that those R beta modules are derived and beta equivalent. Yeah. So in fact, well, in fact, when we change this beta parameters gives you a like a better structure, a richer structure. It defines so actually beta gives you a like a real variation of the difficulty condition. So what does that mean? So first, stability on this. I mean, you fix the beta, then as well gives you your algorithm are beta. If you fix the beta, it gives you a real variation stability on this like calculated category DG category. So, and what does this mean? Basically, it means that like you have a family of we call it central charge from the K group of D. We denote this category by D. R, it's a real family. Also there's some like P structure of yeah, I should say here with I leave. Maybe here on my parameter space the leaves in R to the vector space here R to L. Yes, thanks. Yeah. And so this is that you lift beta to R is originally it lives in S1 and then it's going to it's L to P structure. And they satisfy some other compatible condition. Tell you how that defines this law. So first, well, which is alpha between like so after notation, this L is going to be S1 to the N, yes, and then element here also here this is actually the configuration space. So like black point on your S line, right? Because the recall that the restaurants the positions of restaurants are fixed and you only change it, but you are allowed to change the like the position of black strap. And then if you fix such an element, then there's another important element you see, or beta, which is defined with the following. Well, basically it's very simple, which is where am I? Here. Vertical right strands, and then the position of black strands are. Yes. So ours is vertical, but this is like alpha 1, alpha 2, alpha 3, alpha 3. So once you fix your position of black strands and you make everything vertical, that's an important element here. But you remark is that this is not the identity here, because you can have like different alpha. So in fact, this configuration space is cut into small blocks, and if you add up all those different alpha, you get the identity. So whenever you have here you have an island, and this Z beta now is defined with this integral. Well, this it takes values of n it looks very weird. So ER times that. And I consider, sorry, I should consider the dimension. Okay, and integrate over alpha. That's like the central charge. So, well, how do we understand this? Let's say, so, well, I mean, if you fix beta, then this L is into use this word all followed by the walls. The words in this case all like beta is 0, they are going to be ij ik minus beta j. 我来顺柚子that L
So if it's the things we changed are alphas.
Yeah, now this is the configuration space of alpha. So I'm changing alpha here because I'm doing this integration. So I'm changing alpha.
I mean beta ik minus beta jl is some fixed.
Oh, sorry. This is not. Oh wait.
Maybe alpha equals beta.
Oh yeah. Alpha equals to beta. Oh, maybe this maybe J I K. Yeah, sorry. Basically, this means this black strands hit the right strand. That's not allowed. So whenever this happens, then they'll hit a wall. And this walls will cut your oh, now I should go this.
Yeah.
Very good. Yeah, we are.
So this is my L, and then it's cut into small alcoves by the walls. Right. This is the configuration space of alpha, and this integration basically means, well, I mean, this dimension remains the same in the same small block, right? So actually, it's this function is like piecewise constant, but you're adding them up, weighted by the volume of each small block.
Your voice constant on which wall?
Of course, because because this element is the same, right? If you do not hit the wall, if you just like change your alpha like a little bit locally, and then this element is the same if you do not cross
I
it.
think it's different. Like if you multiply, I mean, I don't know if you. It seems that if you multiply these two elements, wait, they. Yeah, like we did discuss stacking. In my opinion, if you stack and the strands don't match, you just get 0.
Yeah, it's 0. But wait, but don't you define this graph up to isotopy? If you are like stacking this with another thing, but this, well, like the point, the configuration of this point on the S1 is like isotopy.
So
However,
isotopy can move. So it works not only on the inside but also on the top and bottom.
Yeah. So if you just move this a little bit, right, and you to here, and then you can still multiply. So like this strand is the same, like this element is the same as this element.
Okay.
So
Yeah, this is true, but yeah, okay.
I mean, it's just basically if you change alpha a little bit, it's just it's isotopy to the original diagram. I mean, if two diagrams are isotopic, then they are the same element. If you do not hit the wall, then the diagram of this element are like isotopic. Oh, sorry. Here the red strands are fixed. I'm moving the black strands. So this is an alpha. If I move my alpha a little bit, then I will get an asymptotic yeah. Oh, sorry, asymptotic diagram.
Okay, so
I
sorry,
guess.
and here, so
And here is the K yeah, just like the K group, like the positive K group.
yeah. So like you choose like just
Uh-huh.
I mean, just the module, like
Uh-huh.
not on D, but
Yeah.
So
Yeah,
it's also small.
but I mean, I only to define this beta,
Yeah.
define it on the real modules, and yeah. And then so, well, so this is like a torus. You cut this torus into like small blocks, and then you add this integer up, but weighted by the volume of each small block. So this is like a combinatorial way to define the central charge. And then so Aganagic has some physical. She has some physical description, and Von Webster claims that they should match up. And then, well, so we'll cross the wall, right? This is beta and beta prime. Whenever you cross the wall. Sorry, what? Oh, these are walls for alphas. Sorry. Yeah, these are walls for alpha. Maybe. Oh, I see. Sorry, I should draw a different diagram. I should draw a different picture. So maybe okay. This. So you have some walls. Yeah, this is confusing. Okay, so what's using R L? Well, this is the configuration space of beta. Don't know, like beta ik minus beta L. And then this means that well, you will have a wall with like the longitudes of two restaurants are the same. So when your restaurants match cross each other, you will have a wall here. Yeah. And then maybe the pictures like this. Somehow you have a beta, and then you have a beta prime. Right. We'll cross this wall. Oh, I should mention that actually here this definitions yeah, so what do I want to say here? It depends on this oh yeah, so when we will this function remains the same when we cross the wall, so it's actually well defined. When your beta cross the wall, right? Because this yeah. So I will think what I want to say. So you'll have this, but here M leaves you in your then this is like D are beta. If you have a different beta, if you have a different beta, yes, then you have a different. Then you have a different central. Well, yeah, your central charge depends on your beta. Wait, but I thought there is some like you should show some well defined here.
Maybe it's 0 on short exact sequence. Maybe it doesn't depend on beta in a single
Yeah, maybe.
chamber.
Yeah.
It sounds plausible, but it's result of
Yeah, perhaps, yeah, thanks. Okay, so and then we'll cross this, recall we have this this functor, right? This like b beta prime and derived tensor makes sense, b of beta. Well, here I only consider bounded derived category, so beta. Well, so this is equivalence category, but this do not preserve T structure. So we'll cross a wall. We will cross a wall. Your T structure will change. Basically, that's how the well how do you define, how do you give this tau? So then this gives you a tau. This does not preserve T structure. So, well, I mean, if I want to say this, really, really rigorous way, so somehow I should fix our beta, or like fix the block here, and then, well, whenever I cross the wall, I'm like pulling back the T structure here to here, right? So this gives you a so this gives you a map from this the configuration space beta to T structure, to a T structure on my category. And then whenever you cross this wall, this T structure is changed. So this tau is like locally constant, but only changes when you cross the wall. Still, so probably now we should say now homology. From Coulomb branch. Which one should I use? That one?
Yeah.
Okay, thanks. Any question? So now I can consider we should consider the tangles on the cylinder. So maybe cylinder. So this category is defined by objects that just points on the S1, and morphisms are given by this side is due with this one. It's the same. It's like rectangles, right here. When R is the cylinder, it just leaves on the yeah, it just leaves on the cylinder. My tangles leaves on the cylinder. But the claim is that the morphism are generated by the extended Fourier group, which is SI, which is and also I have a sigma, which is I'm like twisting everything from value to this graph here. So it looks like this. twist everything, and then the relations well, the Euler relation for Brady group, but I have one more relation, which is theorem is that Coulomb branch gives a functor from this tangle category to the two category like categories. So I have we have such a functor to given by there is given by this full branch of the KLRW algebra. And, how it is done? So well, I'm very well if I have an object, it's kind of like straightforward, right? So I'm viewing this point as my beta. So such an object is sent to derived category. The position at this point is my beta. Our beta. And then this S, so it's I, which is S. So this is sent to, well, this bimodule, because this gives a bimodule. This gives you a bimodule. Prime. That's so this is like in that language it's like you hit a wall, you cross a wall, you have a isomorphism between and then also you have this element which is twisting. Well, I mean the same, right? It's given by this is sigma. Well, it's the identical, the same picture, but you should view this as bimodule like cKLRW algebra. Then this is a functor between these derived categories. Sorry, the guy. Right, too large. Huh?
No, okay.
Oh, okay.
That's good, interesting.
I think so far. But maybe
We want to continue break some point and then you could continue up to 6.
oh my, I don't have that much to. I mean, I could, but it's yeah. Sorry, I feel I prepared some like vague ideas and sorry, there's no rigorous math. But I mean, do people want to break?
I mean, if you plan around hour and a half, then I guess.
Oh no, I'm not that much. I mean, I'm going to talk very briefly about homological mirror theory, but it depends on like how brief it could be. So I'll finish at 5:30. Yes.
Oh.
Okay. Okay, so let's continue. So the hard part is this, right? So let's send to where. So yeah, right. So how do you well, yeah. Well, so what's what's the like image of this cups and caps? So and so if you want to define that algebraically, it's kind of it's a little bit difficult, but geometrically it's indeed very simple. Uh, you just allow this kind of you allow some like collapse of strands like this. Maybe there are some dots here and others. And this is this gives you a phi module from well here is beta, here's beta prime, like but the number of points on beta prime is like two less than the number of points of beta. So that gives you a derived category. R beta is the derived category of R beta. And then become is a similar. Oh, but so the theorem of basically everything I said here is result as the Webster. But these diagrams, this is a well-defined functor. From cyclic tangles to the category, the C-linear category. So maybe the hard part is kind of obvious that this like that relation, the relation of this graded extended graded groups satisfy, but maybe the hard part to show is this is like this one composed with this one. To be honest, I don't really I didn't really like read his proof of this part. Yeah, I don't know how to show this. So yeah, because you could have a collapse of strengths like this and collapse of that, and you want to show that you compose this one, and then you get this is like the regular KRLW. I don't know how to do this.
So this is modular of usual categories. Also, on the other side,
sorry, what do you mean Euro category?
like I mean, usually it seems two category.
C-linear. Yeah, C-linear category. Or maybe because the image of this category is actually some DG category, C-linear DG category. Yeah. So probably well, because the image is actually very small, it's not I don't need this, but yeah. But I just state it this way. If you like, I can make this category smaller, like I don't know, each category over C, maybe even bounded or triangulated. So here's two remarks. Remark one is that when my gamma is just A1, then this gives you the Coulomb. Okay. And another remark is that this actually like link homology. Not just for links in R2, but links in for links in this cylinder. So for any links in a cylinder, you will have a bi-grade chain contact. Well,
Yeah, it just looks like there was not that much of dependence on the graph.
on the graph.
So
Why is there not much?
I don't know. It's just it looks the same when you have any number of black strands, any number of red strands.
Oh, I think it must have something to do with this one, this one. So because I think like for here you have to like specify the number of like how many strands are collapsing, and that number depends on your graph. And actually, my graph can only be ADE type, so there's not so many graphs. Yeah, and each of these red strands are labeled by vertex. So
here,
so here is like you're like connecting two strands but labeled by some vertex. So this the number of like how many strands are collapsing would depend on your graph, would depend on like these two vertices. So for different graph, you do get different numbers. So for last several minutes, I want to give a very brief introduction of the another side of this story, which is homological mirror symmetry. So by Aganagic's picture, she claims that there's a equivalent to algebras. This is like the A side, and it's equivalent to this. The B side, this is the Coulomb branch, and so hopefully this Gus is teaching us next quarter, and I think this is also one of his topics. So maybe someone will give a presentation on this next quarter. But now, to briefly expand what is her idea. So why is like for syntactical. Right, so and then this category, so objects are just Lagrangians inside Y, and then the morphisms concept between two Lagrangians, the linear combination of the intersection points of L1 and L2. Probably an example like two-dimension example in two-dimension like Lagrangian set just some curves. And then this is my L1, L2, the intersection P1 and P2. And then this is DG category or A infinity category. So there is a differential on each home space. The differential is given by counting P homomorphic curves. Here, 1, P2, So you will find there's spongy homomorphic curves look like this. So partial P1 is P2, and then so B and compositions are given by complete homomorphic curves. Now that is picture. My y is going to be some kind of like Coulomb branch. Maybe it's given by also given by a quiver, and then this is like the dimensional. Maybe here d is our data, and then it's going to be directional equivalent to symmetric product of 6 star A. Oh, no. 1, 2, 1, 3. And then what's important is that there is a like super potential W, which is can be viewed as Morse, holomorphic Morse function. And then for this when we have a pair, then you can define a rough maybe Cylindrical category is Y and W. It's defined in the following way, as well, this is your C, right? And then there are some critical points with W. This is like a critical point with W, and the regular point would be a smooth submanifold, something like that. And the critical value will have singularities. And then there's a parallel transportation. Since this is symplectic, you have a natural connection called symplectic connection, so you can do parallel transportation. And then some submanifold will contract to this point, this convention cycle. And if we look at the trajectory of this convention cycle, then it would be a Lagrangian. So if you have a path here, then leaving above this path, so starting from critical point, and then you draw a line, and leaving above this line, there will be a Lagrangian. We call this gamma. Well, so this is and in fact you have different critical point, and then I'm going to draw a line to positive infinity. So for each critical point, I draw a line and connect to positive infinity. So this category is some category defined this way, but the point is that it is generated by this gamma. This is called Lagrangian symbol. So in fact, it's more than that. These Lagrangian symbols will form a full directional connection, and its mirror is going to be something called like tilting bundles on the Coulomb branch. So okay. So sorry. Oh no. I'll just write one last thing, and that's the end of our talk. So the claim is that the theorem recently proved by I don't know, 9 people, Aganagic and collaborators, right? And it's that this cKLRW algebra we invest into this of x on the B side, we invest into this category. of, of A side. And the conjecture it will be an equivalence. That's and all this not so all this like not homology theory has a A set version. So you can define everything on the symplectic side and they should match up. On the symplectic side, it can be viewed as generalization of Higa floor, something like that. Everything should match up on the two arguments. That's all I like. That's all I want to see. Thank you.
Any questions?
No. No.
And Mingyuan,
Yeah, thanks for organizing. Yeah.
oh, yeah, I had, do you hear me okay?
Yeah, of course, yeah.
Oh, great, thanks. Yeah, but so I had a question about this last statement. So my recollection is that they have some candidate for a sort of projective generator, but they can compute the endomorphism algebra, but they don't know that it's generator or something.
Yeah. They don't know if they generate. So I write like embedding there. It only embeds into this
Right.
category, but they don't know because it doesn't match up with the Lagrangian symbols, so they don't know if it generates the whole category.
And what kind of object is this generator they have again?
Oh, that's sorry, that's very complicated. And
okay, no worries.
They draw this diagram on this torus and
yeah. Okay, it's a topic for next quarter. Yeah.
Probably
Yeah.
next quarter someone will talk about it.
Sounds good.
Yeah, thanks.
Yeah, thanks, Mingyuan. That was great.
Yeah, thank you for coming.
Yeah, sorry about the connection. It was horrible, but yeah.
No worries, yeah. Okay, yeah, bye.
Oh,
Okay, see you guys.
See you.